So moving on, how does this translate into actually inferential statistics? Well, again, just as a reminder, if you're watching this in various segments, um, our sample mean, so when we randomly pick a number of participants or scores or whatever it is from a population, um, those are not going to be equal, probably not going to be equal to the actual population. Okay? If I randomly draw heights from the population of men, let's say the population mean is 5'10", well, I'm probably not going to get exactly 5'10". Probably going to get 5'9", 5'11", as a sample mean. Or maybe less likely, I might get 5'7", and so on and so forth, like we just talked about. Well, this of course can affect our ability to make inferences about the population, because when we're running any research study, we're not really interested in what happened in our samples, but we're interested in what that tells us about the actual population. So our main question is not, did using a cell phone cause more? Well, it sort of is, but it's not just whether cell phones caused more mistakes in our experiment, but does that actually mean that using a cell phone causes more errors in the population? So if everyone used a cell phone while driving, would they be more likely to make mistakes than had they not used a cell phone? Okay. But of course, our samples don't tell us that definitively, right? They're just, as the name would suggest, a sample of that bigger population. So just because we saw means, difference in, say, means of our samples or our conditions doesn't mean the population's necessarily different. Excuse me. So that's where we get into our inferential stats. So we have what's known as a null hypothesis. This just means that there's no difference in population means. So let's say, again, with driving cell phones, our main question is, when people use cell phones, that would be U1, are they making more mistakes than U2? Well, the null hypothesis there would be that no, those two populations are different. People using cell phones, people not using cell phones are equal. That's what these two mean. Population means. The alternative hypothesis, on the other hand, is that the samples actually came from different populations, and thus the population means are not equivalent. So U1, people with cell phones, are more dangerous than U2, or at least not equal to U2, people without cell phones. Okay? So when we have two levels of an independent variable, this of course means that we're going to compare the means of those two conditions, and we want to know, is the actual population, so if we applied this to everyone, is that actually the case, that it's going to still have an effect? Okay. Is there actually a population difference, and it's not just a sample difference? And we're going to use our stats to figure this out. So, okay, so we talked a lot about how sample means can vary, right? Well, they can vary for a couple different reasons. One possibility is that the actual populations differ. So I'll give you a different example for this one. Say you were looking at the average height. Say we're looking at height differences between men and women. So you wanted to look at whether men are actually taller than women or not. So you drew a sample of men and you drew a sample of women, and you measured each of their heights and compared the two means of the samples. That's what we got here. So let's say that the men are the treatment group and the women are the control group. Well, if you find a difference, there's two possibilities. One possibility is that the actual populations differ. The other is that they don't actually differ. So here's what it looks like when they do differ. Let's say that again, this is the population of women, this is the population of men. Those two are actually different here, which would theoretically result in a difference in sample means, right? If I put the men here and the women here, draw samples from each, if the populations differ, the sample mean should also be different, right? But not necessarily, because the other possibility is that it's just a result of error of the mean, right? Like we've talked about. Because we're randomly drawing our sample, it's certainly possible that we're going to just due to chance get differences in our samples that do not reflect actual differences in the population. So let's say hypothetically, there are no differences in height between men and women, like would be shown here. So by the way, it looks like one, but that's just because it's the same. It's basically both men and women here, but it looks like one because it's overlapping perfectly. So another possibility, so one possibility is again that the actual populations differ. So men have different heights than women on average. But the other possibility is that there is no difference in the populations, and we just happen to draw samples that show a difference. So maybe I just happen to draw, a bunch of tall men, a bunch of short women, but the actual populations of men and women are not different. That's what's shown here. So why are these distributions not identical? Well, again, because of sampling variance or sampling error. Because it's, again, random, we're not likely to draw perfectly equal samples, even though the populations are perfectly equal on average. Okay, so here's what those two look like side by side. Again, so our means are different in both scenarios between our samples. So men maybe have higher heights than women here and also here. But is that actually suggesting that the populations differ? So here it's not, here it is. Okay? That's again what we're getting at with inferential stats. So based on our sample, based on our observed differences in sample means, is that evidence that populations actually differ? Well, whenever you run a statistical test, at least as far as I'm aware, it's going to give you what's known as a p-value. We'll get into p-values and the specific tests we use and all that stuff in a bit. But for now, I just want you to kind of understand the background behind these things and what they're really doing. So the logic behind any inferential test um, is, and what it's going to give you is again the p-value is telling us what is the probability the means of the two samples would differ by the observed amount or more if they had been drawn from the same population. Okay, take a second and let that sink in. So what are the odds that the means of the difference we saw in means between the samples occurred just even if there's no actual differences in the population? You could also think of this as what are the odds of getting the observed differences if our manipulation had no effect? That's kind of saying to some degree the same thing, because our question would be, does the manipulation, hypothetical, two populations, one with the manipulation, one without the manipulation, do they differ? Another way to look at this, maybe more simply, is just what is the probability they only differ because of sampling error? So again, we drew a bunch of men and women and we compared their heights. Well, what are the odds? And we do get a difference, however big or small it is. What are the odds that we got that difference, assuming there is no actual difference in the population? What are the odds that we just happen to draw a taller sample of men or a shorter sample of women? Okay. That's what we mean by this probability or by the p-value, which again we'll get into. Okay. So one more time, what we're looking at here is testing the null hypothesis. So assuming there is no actual difference in the populations, so there is no actual difference in height between men and women. There is no actual difference in using a cell phone versus not using a cell phone for everyone, again, because we were looking at populations here. If that's true, what are the odds that we got the difference that we did, which would again just reflect sampling error, right? All right. So that's what a p-value is. I said it like that, but what are the odds that we got this difference just due to chance, just due to sampling error, the same thing, and the actual populations do not differ? Well, if that p-value is sufficiently low, then we do what's called rejecting the null hypothesis. So usually 0.05 is the cutoff. On the other hand, if it's greater than 0.05, we're going to fail to reject the null hypothesis. In other words, the difference is non-significant. Just let that sink in for a second before I elaborate a bit. Okay. So I don't know, I probably couldn't tell you off the top of my head why things are phrased in such a double negative and confusing way, but for whatever reason, that is the case. So if you think about it, if we draw from our population and we're kind of evaluating what is the difference, what are the odds that we got this difference in sample means, assuming the populations are no different. Well, if that probability is sufficiently low, then we're going to say, no, that's not the case. The samples are not the same. I'm sorry, the populations are not the same. Okay. So let's say we get a p-value that's really low, meaning the probability, we'll use that same example, the probability that we got the difference in sample means between men and women's heights, assuming there's no actual difference in the population heights of men and women, then we're going to say, well, that suggests that the null hypothesis is not correct, right? It's not the case that the two populations, men and women's heights, are equal, right? If that probability is quite low. Again, if we find that the odds of getting the difference we observed in our sample means is very low, well, that's evidence against the null hypothesis. That's saying that the odds that, we would get such a difference in our samples is quite low. So that's suggesting that the hypothesis that the two population means are equal is not correct. Let's see. On the other hand, let's say that the probability is high. And again, 0.05 is just kind of the cutoff we typically use. So if there's less than a 5% chance that we got the difference that we did due to sampling error, then that suggests that our manipulation did something or the populations do actually differ. But higher than that, we tend to conclude that there's not enough evidence that there is actually population differences. So that's what happens if the p-value is greater than 0.5. We fail to reject the null hypothesis, and we say the difference is non-significant. So again, put that in an example. If we find that the difference is such that getting that difference, the odds of getting that difference just due to sampling error is high enough, we're going to say, well, it probably was just sampling error, and we don't actually have evidence that the populations differ. Right? That's what we mean when we say fail to reject the null hypothesis. Again, I don't know why it's phrased this way, because if you think about it, rejecting the null hypothesis would mean we can't say that nothing happened, but we can't say that there was no difference. And failing to reject the null hypothesis would mean that we can't say there's no difference. I don't know why it's phrased that way, but it's kind of just the way it's tested. But I don't know why I have to make it so confusing. But just remember this part. This is kind of the main point, that again, if that probability is sufficiently low, we're going to say, well, it's not the case that the populations are equal. If that probability is too high, we're going to say fail to reject the null hypothesis, meaning the difference is not significant. So we might have seen a difference in our samples, but it's not clear evidence that populations actually differ. Okay. Just on that note, though, we don't say that we accept the null hypothesis. Okay. We either just reject it or fail to reject it. Okay. This isn't. Well, no, it is important. You should definitely remember this, but really just a statistical test just tells, it's again based on probability. So we don't really, that's why we don't really say we accept the null hypothesis. We just say we fail to reject it. We didn't find enough evidence that the null hypothesis is untrue. So we didn't find enough evidence that the two population means are the same. Okay? But we don't say we accept. We also don't say that the groups were the same unless they happen to be exactly the same, which is unlikely. We just say that they're not significantly different. Okay. So, for example, again here, let's say we find that chances are, like I said earlier, the sample means are not going to be exactly the same. But so that's why it's not really accurate to say they're the same unless they happen to be, which is unlikely. But we just say that they're not significantly different. Because again, chances are they will be slightly different. Just the question is, are they different enough to indicate that the population's actually different? Okay. Oh, another thing, we also don't say that the results are or we say that the results are non-significant, not insignificant. There is actually a distinction there. So non-significant just means that they're not different enough to say that to provide good evidence that the populations differ, but that doesn't mean that the results are not important, okay? Which is why we don't say insignificant. The results, getting a null result could still be very important. And this is kind of a tricky point because a lot of people actually disagree about this, but we don't say that a result is more significant or less significant. It's either significant or not. At least that's the conventional wisdom. So if it's less than 0.05, it's significant. If it's greater than that, it's non-significant, but it's not more or less significant at one value versus another. Okay, we'll break there.